Hey, what's up everyone? This video is an example of solving a new problem by first solving a relatively easier version of the problem and then using its solution to solve the actual problem. In other words, breaking down the original problem and using your existing knowledge to solve individual smaller problems and then combining those to get the solution of the actual problem. There are a couple of things that make this problem more difficult than the two-sum problem that we saw earlier in this series. We will see all that in this video. Hey, Bhavesh here, and on this channel we learn and apply various data structures, algorithms to solve interesting programming questions. So if this is your first time on this channel, consider subscribing. Let's first take a look at the problem statement. We are given an array of integers of size n, and we want to find three numbers, say a, b and c, in that array such that they add up to 0. So a plus b plus c is equal to 0. We are not given whether the array is sorted or not, so we have to assume it's unsorted. We need to return all unique triplets of such numbers. In other words, there must not be any duplicates. So for example, 1, 2, 3 is same as say 2, 1, 3. We must not have such triplets in the solution. Only one of these two should be there. Let's take a look at an example. Let's say the input array is 5, -2, -3, -1, 6, -4 and 6 again. In this example, we can see that 5, -2 and -3 add up to 0. Similarly, 5, -1 and -4 add up to 0. Another triplet is 6, -1 and -3. And the last triplet is 6, -1 and -3. But in this case, we must not return -3, -1 and 6 twice, one with this 6 and another with this 6, because this will lead to duplicates. Only one of those two triplets should be in the solution. So our solution will be 5, -2, -3, 5, -1, -4 and 6, -3, -1. Alright, to begin with, let's not worry about the duplicates. And let's see, if we are to do it manually, how will we do it? One simple brute force solution can be trying out all possible triplets. So 5, -2 and -3, then 5, -2 and -1, similarly 5, -2 and 6, 5, -2 and -4, 5, -2 and 6 again, and then 5, -3 and -1, 5, -3, 6, and so on. And finally we will check 6, -4 and 6. There are roughly n cube number of triplets that are possible out of array of size n, and hence the time complexity of this solution will be big O n cube. Let's think about another way. We already have solved an easier version of this problem, that is a two-sum problem. This problem only asks for one more number on the top, so let's assume we can solve two-sum problem and we have that API ready. How can we utilize it to solve this problem? Maybe pause the video here and think about it for a moment. Alright, we want a plus b plus c to be equal to 0. What if we fix one number at a time? So let's say we fix 5 in the beginning and let's call it a. Now we want b plus c to be equal to -a, so that a plus b plus c when added together will be equal to 0. And this is exactly our two-sum problem that we discussed in previous two videos, where we wanted to find two numbers, in this case they are b and c, such that they add up to the target, where target now is -a. So fixing one number and then solving the two-sum problem on the remainder of the array is certainly one of the possible solutions. Let's quickly take a look at all the approaches that we discussed for two-sum problem and see which one to apply here. To solve the three-sum problem, we are going to solve two-sum problem n number of times. So whatever solution we pick for two-sum problem, we need to multiply the time complexity by n times to get the time complexity of three-sum problem. Okay, the first approach that we saw for the two-sum problem was the brute force approach, where the time complexity was big O n square and space complexity was big O 1. In this case, for the 3-sum problem, the time complexity will be big O n cube that we already saw, and the space complexity is still the same. The second approach that we saw was using a hash map, where we inserted all numbers from the array into a hash map at the beginning. The time complexity of that solution was big O n, but because we were using additional space, the space complexity became big O n. Now, if we are to use this approach for the 3-sum problem, the time complexity will become big O n square and the space complexity will be big O n. Let's move on to the third approach that we discussed. The third approach was sorting the entire array at the beginning and then using the binary search for searching the appropriate numbers. The time complexity of that solution was n log n. So for the 3-sum problem, it would become big O n square log n, and the space complexity is big O 1. And then finally, we looked at the fourth approach, which was a 2-pointers approach and had time complexity of big O n. Additionally, it had big O 1 space complexity. The second and the fourth approach differ only in their space complexities. Second approach has big O n, while the fourth approach has big O 1. But fourth approach needs sorted input, while second approach does not need sorted input. Both will have time complexity of big O n square. As the input array is not sorted in our problem, the only way we can use the fourth approach is by sorting the input first. Is sorting the input at the beginning worth it for this problem? The answer is yes, because the sorting will take big O n log n time, and anyway the time complexity of our solution was going to be big O n square. Big O n log n is certainly a lot smaller than big O n square, and hence even if we end up sorting the input, the time complexity of our solution will still be big O n square. Alright, so we discussed that we will use the fourth approach that we used for the 2-sum problem to solve this 3-sum problem. After sorting, the input would look like this. And once we have the sorted input, we'll fix one number at a time. In the beginning, -4 will be treated as A, and then in the remainder of the array, we will find two numbers B and C such that they add up to negative A, that is 4 in this case. And we will find that 5 and -1 add up to 4. Similarly, 6 and -2 add up to 4. The only question that is still unanswered is that how are we going to handle the duplicates? We will use a simple idea. Let's say there are multiple -4s in the array. Initially, let's say we will fix this -4 as A and then try to find pairs in the remainder of the array that add up to 4. Once we have that solution, then there is no point in trying with this -4 again, because we are going to get all the same pairs and it would only lead to duplicate because -4 as A has already been considered. So what we will do is, once we have considered this -4, we will skip all the -4 and directly jump over A to this -3. This way, there is no way duplicates can enter into the array. We'll use the same thing for B and C as well. And the way when incrementing A, we skipped all the values that were same and directly jumped to this -3 from this -4, we'll apply the same logic for other variables like B and C as well. This way, there is no way duplicates can enter into the solution. Let's take a look at the code now. So let me take the size of the input, so n nums.size, and a variable in which we will save the answer. Let's say answer. At the end we will return the answer. Okay. So now for each element as A, so for int I equal to 0, I less than n and I plus plus. So we are trying out each number as A. Let me put it, create an extra variable, int A is equal to nums of I. What we want to find is all the pairs that add up to -A into remainder of the array. When discussing, we assume that there is an API for 2sum. So let's just build that API. So 2sum will pass the array to it, so nums, but we don't want to pass the entire array. We want to restrict it to certain range, and that range would be from I plus 1 to last index n minus 1. And we already have fixed the current number, so we'll also pass that current number. And this 2sum method will add all the pairs that add up to the answer. So let's implement that method. 2sum vector of int nums int start, int end, and int a we will call it. Whenever we find b and c, we will enter a comma b comma c into our answer. So now we already know how to solve the two-sum problem. That is, while start is less than n, if we forgot to pass the target. So target in this case will be minus a, and that is second last parameter, target. If this is difficult to read, okay, this looks better. So we have got array, start point, end point, target that we want to achieve, and integer a, which is going to be constant. So if nums of start plus nums of end equal to target, in that case enter the answer. So answer dot push back nums of start, nums of end, and a. These three numbers we will insert into the array. Else, now there are two possibilities, whether it is smaller or larger. So if nums of start plus end is less than target, so one number has to increase and that number will be start, and otherwise will decrement end. And this method should be okay for now. A couple of things that I forgot, that initially I need to sort the entire array. So I'll do that, sort nums.begin, nums.end. Yeah, this should sort the entire array. And okay, we are inserting everything into the answer. Now we discussed about avoiding the duplicates, but we didn't reflect that into our code. So we discussed that instead of incrementing by 1 or decrementing by 1, or even here, instead of fixing each number, we'll remove the duplicates. So let me write one method that will do the increment and decrement for us. So I'll just call I equal to increment, and it will take care of everything. Increment, and we'll pass it nums and current index, and it will decide where to go next from here. Similarly, for this start, I'll use the same method, start equal to increment, and I'll pass nums and start to it. For this end, I will use decrement method. So decrement, which will take care of decrementing appropriately. Okay, let's implement these methods. So int increment, vector of int nums, and int current, and similarly int decrement and decrement, and let's say int j is equal to current plus 1, while j is less than, we need to check for the bounds. So let's say int n is equal to nums dot size, while j is less than n and nums of j is same as nums of current, keep incrementing. So j plus plus, and at the end j will be at some index where nums of j is different from nums of current, so we'll return j. In the decrement case, we'll initialize int j is equal to current minus 1 while j is greater or equal to 0, and at nums of j is equal to nums of current, and here we will decrement j. At the end, return j. Alright, so we sorted the input array, then took the size of the input. Then for each number, we fixed it as number a, and then tried to solve a two-sum problem for the remainder of the array that starts from I plus 1 to n minus 1, and we want to find the target sum as negative a, and because we need to add this a or the first number into our solution set, we are also passing this a to the two-sum problem. In the two-sum problem, we are simply finding the two numbers that add up to the target, and the moment we find them, we add it into the answer. The only tricky part is to how to increment and decrement. For that, we wrote separate methods so we can test our solution. One test case is already provided. We can also add so -4, -3, -2, -1, 5, 6, and 6. Now we can run the code. Oh, it gives time limit exceeded error. Somewhere we are not incrementing or decrementing properly. So here we are incrementing correctly and then passing it to toSum. In toSum there must be a problem somewhere. So if start and end equals target, then here. So here we didn't increment as well as decrement. Here it needs to be done. So whenever we find the target, we need to increment the start and decrement the end at the same time. So this was the problem. Now let's see if it works. Well, for our test cases, it's working as intended. Now that the testing part is also done, we can try to submit this. Cool. So let's discuss the time and space complexity of our solution one more time. So sorting this is going to take big O n log n time. This for loop considers, in worst case, it considers each number once. So it is going to at most run n number of times. And for each number, we are going to solve a toSum problem, and we discussed that time complexity of toSum problem is big O n. So this is going to take big O n time, and hence the total time complexity of our solution will be big O n log n plus big O n square. And big O n square is larger than big O n log n, and hence we'll only consider that. So this way we solved the 3-sum problem in big O n square time. For the space complexity, we are not using any extra space, big O1. To summarize, we used our existing knowledge of solving 2-sum problem to solve this 3-sum problem. A key takeaway is that sometimes we don't know how to solve some problem, but if we find a easier version of that problem and try to solve that, we can probably find the solution to the difficult problem by using the solution to the smaller problem. I'll post the link to this code with detailed comments and analysis in the description below. If you haven't watched the previous 2 videos where we discussed multiple approaches of solving the 2-sum problem, you'll find those links in the description below, so certainly check that out. In the next video, we will solve the 4-sum problem, which builds on 3-sum problem, and hence it's going to be a fairly short video because the technique that we are going to use is going to be exactly same as how we solved 3-sum problem using 2-sum problem. I'll post that video on the next Wednesday. So subscribe to the channel and hit the bell icon so you don't miss that notification. If you enjoyed learning something new today, give this video a thumbs up and share it. Post any questions in the comments below so either I or someone from the community can respond. I would also love to hear any suggestions and feedback that you may have. Don't forget to subscribe to Interview Recipes. See you next time and bye for now.